Last time we talked somewhat about the message authentication codes and what it means for a message to have integrity and how do you check for it. And we gave a formal definition as well as an experiment about how to check if a system is what do you call it? Secure, not secure, has integrity or not. Okay. So now we want to look at an example of how to construct such a MAC. And the first one we are going to look at is a fixed length MAC. A fixed length MAC. Okay. So what is the intuition? What are we trying to do? What do we know about constructing a MAC? Well, we need a keyed function MAC since we are looking at fixed length, such that we need a keyed function MAC, which is we are going to assume length preserving, such that well, first, given MAC k of m1, m2, and so on, it should be infeasible to predict the value. It is infeasible to predict the value of MAC k of m for any m not in m1 to m whatever m1 m2 dot dot dot. And have we seen such a function before which does such a thing? Well, yes, we have. Well, if we could choose a uniform function, that would be super great, but uniform functions are rare, right? What we do have is we can let it be a pseudo-random function. Let MAC be a pseudo-random function. Okay. So, how do we construct a fixed length MAC now that we know that we want to use a pseudo-random function? Construction. So, if we want a pseudo-random function, it's going to be length preserving keyed function. So let f be a length preserving pseudo-random function. Pseudo-random function. So basically a block cipher, right? We are going to construct MAC as follows. Construct the following MAC algorithm pi. First, generator. Well, what does the generator do? It chooses a uniform key for f. Choose a uniform key k for f of length n, right? So maybe you want to take input 1 to the n and output a key of length n. What does MAC do? MAC k of m. Well, here's the easy part. We don't need to do something elaborate for this. You just output k of m. Okay. And then for the third part, you just verify k of m comma t. Output 1 if and only if fk of m is equal to t. Since you already know f, if you already know k, you get the message m, you verify whether fk of m is equal to t, and you get that. Okay? Theorem. I'm going to skip most of the proofs, okay? Because there are I'm not going to go into full details as in the book. Like the book has full proper written out proofs. I'm going to give you an image and some idea of why the proof works. Okay? Theorem. Pi is a secure MAC. Is a secure MAC. Proof. Well, proof sketch. Proof sketch. Okay. So let us see what we are doing. Well, the proof is going to be by reduction. Proof by reduction. Right? If we are using a pseudo-random generator or pseudo-random function, the idea is going to be, hey, this MAC, this pi is secure as long as my pseudo-random function f was actually a pseudo-random function. If there was a way to break pi, then that should give me a distinguisher d which can attack f. Okay, so what's the image that we are having this time? Well, this is my pseudo-random function or a completely random function. The adversary does not know which one I'm choosing. Here's my mystical adversary A. Okay. It sends a message M1, gets back at code T1, sends lots of messages MI and gets back TI. Okay. Now, based on this, what do? Well, we send M1, evaluate, and send back T1. We send MI, evaluate, and send back TI. Okay. Now, what the adversary does is it has to send for the final test an M and T. Right? It has to send both of these, and we take the M, send out what should be its proper encryption T star. Okay. If M is new and T is equal to T prime, we get that the output is 1. Output 1. So maybe this is also part of the adversary. So let me just make this part of the adversary. Okay? Whatever. Forgive my horrible drawing skills. If you really wanted. If okay, so this is what my adversary is doing, and it is using somehow the distinguisher D to do this, right? So here's how the analysis of the proof is going to happen. Okay, when D interacts, how's my TI computed? TI is computed by just looking at fk of m, right? So when D interacts with fk, it doesn't know if it's interacting with a uniform fk for uniform k, or with an actually random function, right? The view of the adversary, is identical to its view on a real Mac experiment. Adversary is identical to its view on on the real MAC experiment. Okay, so what is happening? Well, the probability that D of fk outputs 1 is equal to probability that for the experiment forage of the adversary A, I'm just going to call it A pi, not adversary pi. A pi of n is equal to 1. Okay? Now, compared to that, when D interacts with an actually uniform F, when D interacts with uniform F, then seeing F1 to Fm, M1 to Fmi, it does not actually help predict Fm for any m. Does not help predict Fm for any m in M1 to Mi. Right? There's no additional information if F is completely uniform. It's going to choose a random Mi, and it's going to choose a random output for given any m. And so even if you know F of M1 to Mi, it doesn't really help for something else. So the experiment is going to succeed. Probability of the F outputs 1 is smaller than or equal to 2 to the minus n. Okay. So in the first case, you are going to if you can break the function f and figure out, oh, wait a second, this is my function, this is how the output, then I can succeed with probability 1, right? Then I can actually succeed. If I can't break it, then my experiment is going to fail. In the second case, you are only going to succeed with probability 2 to the minus n. However, if my f is actually a pseudorandom function, since f is a pseudorandom function, the probability that I will be actually able to distinguish that, oh, wait a second, this function is being pseudo-random and this should be the output, is actually negligibly different from this, the probability that you are successfully able to guess on an actual random function. So probability that dfk outputs 1 minus probability that df outputs 1 is negligible, so less than epsilon n. Right? So let me just fun df. Okay, and therefore, moving things around, I get that the probability that moving things around and using that the first term is equal to this, I get probability that the experiment forge adversary a pi of n succeeds is equal to the probability that df outputs 1 plus epsilon n, right? Which is smaller than or equal to is smaller than this. This is smaller than this, which is equal to which is, let's say, smaller than or equal to 2 to the minus n plus epsilon of n. Okay, and hence is also negligible. Okay, therefore negligible. And that's the idea behind the proof. Like, if you want the full rigorous proof, you can read it in the book. Okay, but here's the basic analysis of why the proof works and how the system is being set up. Okay, so what are the major drawbacks? I've created a fixed length Mac, and what is its major drawback? Well, it's fixed length, so it only works for that fixed length. This works only for fixed length, only for fixed length messages, right? And the other problem is the length is actually the length of the block, right? So, and the block length is actually quite short. This only works for short messages. Generally, when you're encoding stuff, the block length is quite short. For example, if you use the AES AES encryption, which is, what is the full form again? American Standard and American Encryption Standard, AES. Advanced Encryption Standard. My bad. Advanced Encryption Standard has a 128-bit block size. As 128 bit, not even byte, block size. Okay, which is really small, right? So that means I can only do really short fixed length messages. The construction only works for short fixed length messages. Right? So how do we make this better? How do we improve? How do we improve on it? Well, the idea is going to be we use this to build one for variable length, right? So how do we construct secure Mac for variable length messages from a fixed length Mac from a Mac for fixed length messages. Well, let us try some things. Okay, what is the easiest idea we can think of? Let's see if that works. The easiest idea we can think of is easiest approach. Well, just use Mac of Mac well, prime of M1 to M, I can't use T. Well, let's say ML is equal to Mac of K of M1 dot Mac K of ML, right? And we can say, oh, verify if and only if M1 to ML, T1 to TL is equal to 1, if and only if the standard verify, so this should be verify prime of K, if and only if the normal verify K of MI is equal MI comma TI is equal to 1 for every I. Right? Great. This sounds like something that we can try. Right? And the problem becomes, is this secure? Is this secure? And the counterexample is as follows. Suppose I send a message M1, M2 with tag T1, T2, right? Then the attacker can send A can send M2, M1 with tag T2, T1, and that will pass, right? It would be a fake message from someone, but that is passing. So need to prevent block reordering. So need to prevent block reordering. Okay. Let's just say, okay, I want to prevent block reordering. Let me do the following. Next approach. If I want to prevent block reordering, I just add what is the block. Okay. With each message, I will tell it, oh, it is this block. Okay. What does that mean? Compute tag ti is equal to mac k of I with mi. Okay, so in a way, you are telling it that oh, this is the first block, this is the second block, this is the third block. So even if you reorder them, it's not going to work for every I. And output tag t1 to tl. Right? Well, this does not stop a truncation attack. Does not stop truncation attack. What does that mean? Example, if I send a message M1, M2, M3 with tag calculated this way as T1, T2, T3, then A can send message M1, M2 with tag T1, T2, and that would be evaluated successfully. And that's a problem, right? So now we want to prevent it not just from block reordering, but also from truncating. Okay. Well, let us say next approach. Let's say I'm going to add one more block. I will say that I will add that this is the total length of the message. Okay, in every block I will say this is the total length of the message. If you see any other random length of the message, that is wrong. Okay, so compute ti is equal to mac k of, well, l with I with mi, where L is the length of the message, where well, I've been using L for the number of blocks, so maybe I should use some other thing. And let me just use D, whatever. D, where D is the length of the message, in bits. Okay, great. Now output T1 to TL. Right? And again, there is a problem. This fails to a mix and match attack. Fails against a mix and match attack. What is a mix and match attack? So suppose you have seen messages, sent messages M1, M2, and M1 prime, M2 prime with tags T1, T2, and T1 prime, T2 prime. Okay. Then the adversary A can send a message M1, M2 prime, and it will be verified. Okay. And so, in all, I need to prevent all three of the things. So need to prevent well, first block reordering, truncation, C8 truncation, and mix and matching. Mix and matching. Okay. So what we can do is say, okay, I am going to add in one more thing and make sure this works. Okay. What you can do is say one solution is to create mac k m prime of m1 to ml is equal to hoof r mac k r l 1 m1 mac mac okay, well, let me write it in the next line. ml is equal to r mac k r l 1 m1 mac k r l 2 m2 dot mac k r l m1. Okay. Woof. Where R is chosen uniformly. Okay. Where R is chosen uniformly. And what does verify do? On each tag, it outputs if it checks is the total number the same, is R matching, is it the mth block, and stuff. Okay, so it's going to be a really long process. Okay, and well, clearly it's not a great solution. Not a great solution. Not a great solution. In particular, it's not very efficient. Not very efficient. Okay, so can we do better? Can we do better? So I'm not proving that this construction is actually safe. and secure. Okay, that's in the book. It's not something that is super relevant to things, so I'm skipping over the proof. Okay, so can we do better? And the answer is yes. Well, we can do better by using some of the techniques that we learned before. For example, the CBC. So uh, let's look at the basic CBC. Okay. How does the basic CBC Mac work? The construction is in the book. I am going to give you a image construction and maybe write down what the thing is. Um, you take the message 1, okay? You find a function fk, right? Here I'm 1 with fk. Great. It is length k, so things match up. Now, you take m2, you XOR these two, get your output, and use that as your input for fk. M3, and so on, dot dot dot. So ML, FK, and in the end, you are going to get some tag which you're going to call T. Okay. So generally, what you're going to set is let T set T0 is equal to, let's say, 0 to the n. Okay. Then for I is equal to 1 to T, 1 to L, sorry, 1 to L, set Ti is equal to Fk of Ti minus 1 XOR some Mi. Okay. And then you output only the final TL as the tag. Output TL as tag. Okay. What does verify do? Verify repeats this entire process, calculates TL, and says, okay, I am going to output 1 if and only if TL is equal to backup. If and only if it matches the tag T, right? And this sounds great. This works. Okay. We are not going to prove that theorem. I'll just say it. Theorem. Let L be a polynomial. Let L be a polynomial. If f is a, if f is a pseudo-random function, then the above construction, is a secure Mac, Mac for messages of length lfn times n. Okay, because, well, f is going to output some L of n as the block length, and sorry, what is their L that they're using in here? Their L changes. They're just using L for L of n. Okay, so let me just, well, whatever. So L here is L of n, whatever, doesn't matter. Might be confusing, but just keep in mind that it is L of n. Okay, had me confused for 1 second because I'm using a combination of notes. These are not just following the book. I'm using this theorem from the book, some other things from somewhere else. Okay, so let us see how it compares to the CBC encryption that we saw before. Clearly, things are slightly different, right? The biggest thing is there's no initialization vector. So CBC MAC versus CBC encryption mode. Well, the very big difference is CBC MAC is actually deterministic. Okay, there is no initialization vector, and if you send the same messages, it is going to have the same exact tag again. Okay, that's because, well, in the definition of MAC, you don't need it to be randomized to be secure. MACs do not need to be randomized to be secure. True. RE. Okay, the threat model and stuff is different. We are saying that, we are ignoring repeat attacks, right? So there's no need for randomization. And verification in that case is done by recomputing the result. Is done by recomputing the result rather than computing it backwards, right? As in CBC mode, where you had to start off from the back, calculate F inverse K for every single term to get things. Here, you have the message, you have the T, you know the F, the K, just calculate the entire thing, check if it matches, right? One more thing is, in CBC MAC, only the final value is output. Only the final value is output, right? Which is what is making it truncation secure. If you were giving it the entire thing, you could truncate it anywhere and that would work. But since you're only outputting TL, it is secure against truncation, right? Now, if you wanted to have security as well as what do you call integrity, then you'd have to use both, right? You can't get security from CBC MAC, you can't get integrity from CBC mode, so both are essential for security. Both are essential for security. Okay. Well, it's also that if it is actually non-deterministic, which is to say, if there is an IV initialization vector that you're choosing randomly, then you can actually show that that is not secure. So it is secure only if you have no randomized vector, as in to say it is deterministic. Okay, so both of these properties are also, so I think I misspoke initially a bit. The security here is only talking about integrations, security in terms of integration, security in terms of integrity. Okay, and both of these properties, which are not more or less, let me call them 1 and 2, both of these, which are very different from CBC mode, are in fact essential here for integrity. Okay. Once again, I am going to skip the proof for the security. Okay, but I will just say that once again, the system is secure as long as, yeah, as the theorem says, the system is secure for as long as f is a pseudo-random function of log length n. Okay, and it is also only secure if both the sender and receiver know what the parameter L is in advance. The sender and receiver must agree on the length parameter L in advance. Okay. If you try different things, it's not actually secure. Okay. Now, the standard problem when we saw CBC mode was what happens if your message is not of length multiple of block. Okay, so in that case there are several ways to actually handle extensions. So CBC Mac extensions, which is to say what to do if message length is not multiple of block length n, right? And the simplest way, and there are several ways to handle this, the simplest is actually, unlike what is it called? Unlike encryption, where we padded the message at the end, this time you actually prepend. So one of the simplest ways is to prepend the message length before applying basic CBC. Applying basic CBC Mac. Okay, and here's how it's done in terms of an image. You take the length L, go through FK, you get your output, hit it on M1, FK, M2, FK, dot, ML, FK, and you get your ciphertext, not ciphertext, the T. Okay.